Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Folks, thank you very much for coming, to all of you, and for the virtual audience out there. Thank you for joining us. It's a pleasure to have again our friend and close colleague Richard Ladner from UW, presenting yet another very interesting talk on MobileASL. I'm not going to say anything more about it. Don't want to steal the thunder, but I just want to say a couple words about Richard, whom we've collaborated in many projects. So it's very nice to have the opportunity to have you here again. Richard is a professor at computer science at the University of Washington, and a very well-known name in the field, with many awards and a very long career. Just celebrated your 35th anniversary at UW. Congratulations. And he's a fellow of the ACM. He's chair of the ACM Special Interest Group on Algorithms and Computation Theory, editor and associate editor of many journals, a very well-known name, and it's a real pleasure for us to have you again. Without further ado.
Thank you, Rico. I'd like to mention also that Rico has been a great contributor to the University of Washington. He taught data compression 3 times in the last 6 years, and Rico was very kind to give a lecture on audio compression. And I tried to thank him by sending him a little card, but this is what happened when I tried to send him a little gift to thank him, and it was returned, but I finally was able to give it to him today in person. So anyway, what we're going to talk today about is American Sign Language and making American Sign Language accessible on cell phones. So American Sign Language is the preferred language of perhaps 1 million people in the United States and most of Canada. There's a different sign language in England and New Zealand and other English-speaking countries because American Sign Language has its own origins. Its origins are not English. Signs usually occur in the sign box, which is around the body, about that big, around our friend Jessica here. Jessica is signed like this, because she'll show up again. So, and signs are composed of, as you can see right here, I have a good demo, location, orientation, shape of hands and arms and movement and facial expressions. And as you can see, it's usually used with 2 hands, although she can demonstrate for us that you can also sign with 1 hand. So current technology for deaf people, well, the TTY, it's a little antiquated now, but most deaf people don't use it because I'll tell you why in a moment. They have actually sidekicks and BlackBerries, and so that's sort of taken over from the TTY. Although the TTY is still necessary because if you want to call the government, or if you want to call 911, or you want to call a business, they still use TTYs. So many people have TTYs in their homes and use them, but it's not the preferred thing to use these days. The benefits are low bandwidth and they're mobile. So, for example, the sidekicks of BlackBerries, you can put them in your pocket. A problem is that it's slow, it's tedious to type, it's English, it's not ASL, so it's not in the natural language that people would like to use. So what is being used now is video phones, so VP it's called. And there's different modes. You can use it with a set-top box on top of your television connected to the cable system, for example. Or you can use a webcam. Or you can use something like a Live Messenger, Windows Live Messenger, something like that. So it's the big advantage is it's an ASL. And I've used it myself in talking to deaf people, and it is much better than using a TTY. It's much faster, it's more natural, and communication is clearer. The problems are that it requires higher bandwidth and it's not mobile. So a mobile version of this doesn't exist. So our goal in this project, and we have some members of the team here actually. I'd like to introduce Eve Riskin, sitting right here. Just wave your hand. She's a professor at the University of Washington. Rahul Venom, who's a graduate student in EE. Neva Chernyavsky, who's a graduate student in computer science. And Anna Cavender, who is a grad student in computer science. So it's nice of them to come, and their names will come up, and I'll talk about them later. So we'd like to use ASL on, I don't have my cell phone with me, but on a cell phone. We all have cell phones now, except for maybe these three gentlemen up in front who are deaf. May not. They might have them actually because you can still text on cell phones, but they don't use the video capability. So the challenges are, well, we have limited network bandwidth. So the cell phone network uses pretty low bandwidth, maybe 10 to 50 kilobits per second. It's limited processing power on the cell phones. Turns out to be an additional major challenge, that it's not a full computer. So you have a picture at the bottom here showing somebody talking at one end, going through the cell system, and somebody receiving at the other end, and they're talking to each other in a very natural way. Oh, this is a very crude diagram, but so there's going to be a cell phone, and this is the architecture, the cell phone interface. It has a camera, and hopefully the camera is facing in the right direction, unlike the current cell phones that exist. It's facing toward the screen as opposed to away from the screen. And such cameras do exist on some cell phones, particularly in Europe and Japan, Korea, and places like that, where they do have this capability. We have a encoder which compresses the video, because you have to compress it to a very small amount so that you can send it over this very small channel. Then you have to transmit it over the cell network, and then on the cell phone you'll also have a receiver, because you want to be able to receive the call and then decode that compressed signal and then play it back. And all this in real time, meaning that it's natural, there's a very little delay that occurs in the conversation. So our constraints are, well, the reason we started this project is basically fair access, that we'd like to be able to have in the United States, where we have these limitations in bandwidth, the ability to have real-time video phone over the cell system. So we want that as soon as possible. We could wait until 3G happens and just use the existing systems, for example, in Japan and Korea and in some European countries. But why should we wait? Why not do it now? And whatever we develop here, especially the data compression part, will be useful at high bandwidth as well as low bandwidth. And I'll show you a little demo, not a demo, a picture in a moment of the quality that you actually do get, at least in Japan, because I have a picture of that. And I already mentioned this low bandwidth. 30 kilobits is probably even high. We probably should say 10 to 80 or something like that. And trying to get these numbers out of the cell phone people is like not possible. Low power, well, you don't want to use a lot of power on your cell phone because you have a battery. And low power means not too much computation if you can avoid it. Now there are these new mobile broadband services out there like DCAS from Verizon, and I think T-Mobile has one and Sprint has one, and they all have them. But basically they're higher bandwidth for download but not for upload. Well, if you're going to transmit from a cell phone, you need high bandwidth, or it seems like you might need high bandwidth upload as well. So this is, what about 3G? Well, this is a 3G network. This is from Japan, and this is a picture I took. You can see me there with the camera taking the picture with the white hair and the box on the right. And that is a pretty accurate, unfortunately my flash went off, so there's a big white spot there. But it is a blurry picture. And I don't know if other people have visited foreign countries or know about these systems in foreign countries. It's the same everywhere, but my experience, my personal experience with these phones is that right now they're not very good. They're okay, and people can use them for sign language conversations and do in Japan and other countries, but it's still pretty blurry. Also, there's I don't know, call it a Microsoft product called Portrait. It's a special codec that was developed by Microsoft Asia. It's very low bandwidth, low power, small size, The video is very tiny. It might not be suitable for sign language. And I was talking to Rico this morning, and I think he agrees with me that it's basically it's so low bandwidth that it's just doing outlines, and facial expressions, for example, don't come through. So before I go on, this is getting a little technical here. I was thinking that it might be a good time for Anna. Could you turn on the? Oh yeah, just start passing that around. So we have the kind of video that you can see that we're producing on these small devices. So we decided to use this H.264 standard. We're going to try to use a standard because in cell phones they're now building decoders, H.262 decoders in hardware. So we might as well take advantage of that, and just take advantage that there is a standard. Furthermore, it turned out there was this open source X264 implementation. I don't know if you can read the small print there, but there's the creators of X264, and I've underlined one fellow there, Lauren Merritt, who happened to be a student at the University of Washington, and we happened to get him on our project, so we had sort of the inside scoop on X264. So it really, really helped us move faster in terms of the getting our coding working. So H.264, it doubles the compression ratio over MPEG-2, so it is a lot better. And I think we can thank Gary Sullivan, in part, who's a Microsoft employee, for getting that standard through, or helping get that standard through, because it is an excellent standard. Also, X264 is incredibly fast. And on a 2 gigahertz computer, you can do 1,000 frames a second. It's rapidly fast. Now we're using what's called the main profile, which has some very nice features like arithmetic coding and other features that actually slow us down a little bit, but does improve the fidelity. And finally, the main reason we use it was that we use off-the-shelf H.262 decoder, and there are lots of them out there. It's quickly becoming a standard. So here's sort of my outline. I just went through the motivation and introduction. And please stop me if there's any questions, raise your hand, and I'll try to answer any questions that come up. I'm going to start with some more motivation, which are some user studies. And then we'll talk a little bit about the rate distortion complexity optimization, not very much. That'll be for the sort of technical people. A little bit about our implementation, a little bit about the user interface, and then some of the current and future research that we're doing. So Anna Cavender is sitting over here, has been the main mover on the user interface. And she got together, which is a great idea, a focus group of deaf people in sort of youngerish, not as old as me, and sort of had an open 1-hour session and talked about the physical setup, how you set up the phone, features, what features you like on the phone, and privacy concerns. ASL is a visual language, would be concerned about privacy. Well, people on cell phones don't seem to be concerned about privacy. And some scenarios, riding on the bus, in the shower. Well, I don't know about in the shower, but so the implications from the focus group, I'm not going to go into details, just some sort of anecdotal things. I don't foresee any limitations. I would use the phone anywhere in the grocery store or on the bus, in a car, or restaurant, anywhere. There's no need within the deaf community for mobile ASL. There's no need for privacy, I guess, for mobile ASL conversations. That seems to be a bug. Yes?
So it seems like with ASL I need both hands. How do I hold the phone and talk?
Well, I was going to ask my interpreter to sign with one hand. If you were driving a car.
But what about having something like Dylan had for holding the harmonica? Some way of holding the camera without using your hands.
Dylan? Bob? Oh, you mean put it around your neck?
Dylan had this right.
Did that come up in the focus group, Anna?
Yeah, people had wild and crazy ideas of glasses that showed videos of glasses, or like a thing that you can put on your head and it comes out like this.
Deaf people sign with one hand all the time, though. Like if they're at parties and they're you got a drink in one hand.
Exactly. That was essentially the solution. And if you want to ask me later, I have a video of somebody holding the phone and signing. And
Yeah,
it's
it's on the cell phone.
It's not-
So
I think it's the issue.
my experience is that as long as you have it kind of stable, you rest it somewhere, you can do it. Yes.
So this scenario is somebody communicating with another person who also knows ASL, and they can communicate back and forth.
Okay.
Did you think about, or what about needing a remote translator so that
Yeah.
you can speak to someone who
That's a
does
good
ASL?
question. There are services that exist now for video phones that I described earlier. It's called VRS, Video Relay Service, and it's quite a large business. For example, Sorensen has, I think, 2,000 video relay service interpreters, 2,000 in the United States. So, and a deaf person can use that service for free. So there's some nodding up here. So.
Call that service.
So that service has to become available to cell phone users now. And that would take another step beyond what we're doing, because right now there's no connectivity between, we're not anticipating in this part of the project connectivity between our cell phones and a general system. Just cell phone to cell phone.
Okay.
How
In the
rich
back.
is this language? How many words we have there?
It's, how many words are in your language?
30,000, 50,000 in English?
More.
Okay,
More.
that's a good question. And I'll say this, that sign language vocabulary is quite large. It encompasses everything you want to say, you'd ever want to say. And it can be very technical. There are deaf scientists and engineers, some in the room. So like every language, it borrows from other languages. So it might borrow, like the sign for Japanese is the same sign in Japan. That's the sign for Japanese. Also, sign language has this rich ability to modulate itself. So if you have some base sign, then you can modulate it to give lots of different meanings. So it's not the number of signs, but it's the number of signs plus the ability to modulate. For example, if I do the sign for walk, this is one sign for walk. I could walk uphill, walk downhill, walk to the right, walk to the left. You know what I mean? So the ability to modulate signs in sort of this infinite continuum gives it that richness that spoken language doesn't have that ability. So in some ways it's a better language than spoken language. In fact, lots of parents are teaching their children, babies, sign language these days because they think it's better. So basically, the bottom line is, hey, we're already using video phones. We just want it on a cell phone, that's all. So there doesn't seem to be, the focus group basically says, go ahead. We did some eye tracking studies, and it confirmed what other eye tracking studies showed, that participants watched ASL videos, and we had eye tracker on them to see what they were looking at least what they were focusing on. And a lot of people think that deaf people would be focusing on the hands, but they're actually not focused on the hands. Their eyes are not moving around like that. It's a lot of energy to move your eye around and watch those hands. They're focusing on this interpreter's mouth. So 95% of eye movements are within 2 degrees of the signer's face. And the implications are, I think I should just give you the demo. Let's see. The best thing to do is to, I have to put my glasses on. So the little green dot is from the eye tracker data, and it's showing somebody that's sort of listening to these signs or reading these signs and where their eye is looking. So it's their parafoveal or peripheral vision that's picking up all that gross information about the signs. And you can see that this woman that's signing has using facial expressions, and those are quite important in sign language. So that's another way to modulate signs. And so that's sort of a little proof of concept that that idea is actually working. So the implications is the face region around the head is most important for getting sort of clear vision, because that's what you're actually looking at focusing on, and around can be a little more blurry. I wonder why it's so slow. I guess I should have closed that. Let me close that. Have any idea why? That's Microsoft.
Yeah, you gotta kill the video.
Kill all the videos?
No, oh, no, well, I didn't know if you had more.
There are. Pardon? Well, let's see. Let's stop them then. Okay. That's never happened before, so I apologize.
It's not your fault.
It's always nice to give a talk at Microsoft to have PowerPoint crash. Did I do the right thing? I said don't send? Okay. Okay. So this motivated another study, a user study, mobile video phone study, where we looked at 3 region of interest values. So we took the head and we said, well, we'll just do that at the same fidelity as everybody else. Or we'll put more bits on the head and make it a little more clear, or then make it even more clearer. And you can do that within this H.264 world. We also looked at 2 frame rates, 10 and 15. I wish we looked at something smaller, but it turned out 10 and 15 is what we looked at, frames per second. And then we looked at 3 different bit rates, 15, 20, and 25. And because those are the bit rates we're anticipating, to see if there's any difference between them. We looked at 18 participants, 7 were women, 10 were deaf, 5 hearing, 3 were children of deaf adults, and all were fluent in ASL. I can't remember their average number of years with ASL, but it was, 9, 8. So we varied the region of quality of region of interest around the head. So let's see. There's the region that we might spend more bits on. So on the left, it was sort of everything in the whole video was the same quality, and twice the quality around the head was 6 ROI, and 12 was 4 times the quality.
Excuse me?
Yes.
Are those all the same bandwidth then?
They're all the same bandwidth.
Okay.
Yeah. We didn't change the bandwidth. So now hopefully I can do another demo, and didn't want that. Okay. So which one? This one here, yeah. So let's play that. So you just have to look at one at a time, but the one on the right has the most quality around the head, where the people are focusing on, but the hands and the body and the torso are more blurry, and the one on the far left, everything is the same. And that's our friend Jessica again. 15 kilobits per second for this bit rate. Okay.
You said you tested this with
Yeah, I'll give the results in a moment.
okay.
Okay. Okay. And then we did different frame rates that I mentioned. So the difference here is that it's the same bit rate. So if we go to 10 frames per second, the frames are clearer, but there might be a little bit of jerkiness. If you do more frames, then the frames are less clear. And we also did the whole study on the cell phone itself. So they had that experience with the cell phone watching the video. And the survey was also done on the cell phone. So here's a question. What did she eat at the baseball game? And so this question was part of the study, but we didn't actually use it. We just wanted them to pay attention because they knew where they were going to ask the question later. They weren't just to look at the video, but to actually try to understand the video. And here's the question that we really did measure. How easy or how difficult was it to understand the video? And we rated on a five-point scale, difficult to easy. And these were the results. The first thing we looked at, well, first of all, these results were all independent. That the frame rate, the bit rate, the higher the bit rate, the more they liked it. Well, that's nice. But that was completely independent of the frame rate or the region of interest. And so that first one is completely expected. It's nice to do something where you get exactly what you expect, that more bits is better. The frame rate, well, 10 frames was preferred over 15 frames. And so I'll give you a little bit of example later about that. I'm not going to do the video on this because you can't really tell the difference very much. So it's a slight preference there. And here's the kind of interesting thing, that the ROI, the middle value, that is the one that's more clear but not the most clear on the face, was preferred. Because then there's some trade-off. If I meant everything in the face, then you couldn't read the signs at all. So there's going to be some fall-off. So you should expect a curve like this, worse to better to worse. So we were very fortunate that we hit the sweet spot here, or near the sweet spot. Oops. So the mid-range ROI was preferred, sort of between the two extremes. The frame rate, lower frame rate was preferred because the signs were clear. And things like finger spelling were not lost at 10 frames per second. And everything was independent of the bit rate. So a little bit, yes?
How comfortable were you with your sign testing around having Jessica's signs that were very similar or modulate signs like you just talked about? Because I can imagine that distortion, signs that are similar might get confused. Or sound like if you're doing walk versus walk fast, right?
Well, we didn't test for that much understandability. Like, we only asked that one question and we didn't even use it. We just wanted to pay attention. So we're just asking for their opinion. So we didn't really test anything for that much detail. Maybe Anna has a comment.
Sure. So the videos were about a minute long. So I guess we didn't intentionally have any signs that were similar. We made sure to have finger spelling in every video, at least a little bit. And then I started out with, I think, 22 videos, and I had them independently rated for their easiness or difficulty, aside from any compressions, like the most clear level. And I think 4 of them were rated slightly more difficult than the other ones. So I used videos that were all rated at the same level of difficulty in terms of the language, not the compression. So they should have been all pretty similar.
Yes?
In speech synthesis, and I think in speech coding, it's sort of known that things like rhyming tests, performance on rhyming tests, can be very different from general overall comprehension or desire. So I could imagine that a rhyming test might come up with very different answers.
Yeah, we considered that, but...
I'm not saying it's a good thing or a bad thing, I'm just saying I bet they're different.
But I think it would be very difficult to develop one that's good. Because there are some standard rhyming tests that have been around for many years. I can't remember their names, but that people use, and they were developed over a long period of time.
I mean, some analogy for rhyming in an ASL.
Yeah, there is. I mean, the sign for, this is a sign for candy, and this is a sign for bitter. You know, so They're pretty close, but they mean something quite different. I remember, this is kind of a funny story. I went to a play with a deaf person once, and I met somebody there. It was a friend of mine, and she knew a few signs, and she said she didn't want to sign because she was shy, but she actually said she was a prostitute. So the sign for shy is this, and the sign for prostitute is this. So there can be rhyming tests. So we'll get a little technical now. There are a few technical people here. So rate distortion and complexity. We found out that the biggest constraint that we're having is really the speed of the computer on the cell phone is not that fast, and it has a very difficult time producing enough frames per second. And so we're very interested in trying to find, well, for the amount of frames you can produce, the amount of time you can spend on the computer producing those frames, what's the best fidelity you can get. So for H.264, you have the raw video, and you also have these input parameters that you can put in. And I'll talk more about them. And then you get your compressed video. Depending on the input parameters, you might get a higher quality or less quality compressed video. In general, sort of, if you set your input parameters to sort of a fast setting so things get done fast, you get less quality. But that's not always the case. And if you set them on the high values, somehow on the high values, you get higher quality, but it takes longer. So that's general, but it's not exact. So what we'd like to do is find out about this, and so that we can find the right settings for the H.264 so that we can get the best video that we can get for a particular time. So we have this curve over here, distortion encoding time trade-off. So I guess I can walk up here for just a second. So if I have this much time, I don't want to use this. I don't want to use these values. I'd like to use these values here, in other words. Now, the unfortunate thing is there's 3,360 different settings. So that's a lot of settings to look through. So we worked on a way to try to speed that up. So here's a picture, again, of this. And so these values are actually real values that we found for the various settings. All that yellow is 3,300 approximately points. And this is for 30 kilobits per second, 10 ASL videos. And these are averages. And then this line on the outside is what we call a convex hull. Those are the sort of good settings that you'd like. For a particular time, you want one of those. You pick the one on the convex hull. So we use this GBFOS, sort of varied this GBFOS approach that Phil Chow pioneered, who's in the room, along with Lukabau and Gray. So we're going to choose the input parameters that minimize the slope of the convex hull and repeat. So we have these 4 parameters, and each one of them, if you can fix all the other parameters and just vary that one parameter, then you do get some convex hull. And so we have these sort of 4 that we'd like to pick from. So we pick the best one, and then we repeat that process. Now, that would work normally, but these parameters are not working independently. So it's kind of a distortion of the GBFOS method to do this. But it was worth a try. And we did two approaches. A basic approach was that we just compute these slopes once and just stick with them. And the other one is it's an iterative approach. We recompute slopes after each parameter is chosen. So the results were pretty good. So here we're on a different scale here. We're not on the mean square error scale. We're on the PSNR scale on the left. So higher means higher quality now. And so the convex hull is the blue line, which is the best you can do for a given amount of time. And then using the iterative method, we're almost on that. And even using the basic method, we're very, very close. The basic method only uses 33 encodings instead of over 3,000 encodings. And the iterative approach used somewhere between 81 and 268 encodings. So these are faster methods, and they seem to work fairly well in practice. Now, Rahul did a lot of this work, who's in the room. And I was just asked Rahul, are these averages here? Yeah. Now, those are averages again? So a little bit about the X264 implementation. X264 was developed for Linux, and it's written in C, I believe. So when we ported it to immediately to Windows, it didn't work very well, and so we had to do a lot of changes to make it work better. And one of the main issues was the difference, the MMX technology, going from a PC to the Windows mobile environment or the computer on our cell phone. So we had to do significant modifications. Took quite a bit of time. So this is sort of the summary. So there's 4 bars on the left and 4 bars on the right. The 4 bars on the left are for the screen size that you're seeing in the cell phone. That's compressing that size. And the 4 on the right are for compressing QSIF, which is slightly smaller image and probably not as good. We'd like to do something bigger. Now the blue bars, they go up the blue bars. That's how many frames per second we could. And by the way, among the 4 are the different settings I talked about. So there's a high setting on the left, which means you can't do very many frames per second, to a very low setting on the right there, which means you can do less quality but more frames per second. And so now what's the difference between the blue and the red? The blue is what we could do when we got the software and we did not use any of the MMX technology on the cell phone. And the red is all the work that we had to do to improve it. So for example, for the high setting over here, or excuse me, for the low setting, which is the 3rd bar over, we got up to about 7 frames per second. And that is pretty close to being okay. If we go to the very low setting, the quality gets a little bit worse, but we can do 10 frames per second on a cell phone. Now, of course, we're not spending any time, this is encoding, not spending any time doing decoding, so you have to account for that later. So I thought I'd give a little demo of this, just to show you the difference between these. So the one on the left is a low complexity, done at 7 frames per second. And both of these are 25 kilobits per second, and the 6 ROI, so we are enhancing the face. And maybe I can ask the deaf individuals in the front if they can understand the left one. I think it's pretty good. The one on the right is very difficult to understand because it's such a low frame rate. So we're missing a lot in there. I think somewhere in the middle of this, she's actually doing finger spelling, and there's very little you can catch from it. So you can see right now, realistically, 2 frames per second is not gonna make it. So a little bit about the user interface. There are some basic principles. Should be usable, intuitive, easy to learn, inspired by deaf users, utilize existing knowledge because there already are using video phones out there, so we'd like to use something like that, except it's a small screen problem now. So there were design stages, and we actually, Anna worked with Jessica, who's our star, last summer on developing all this. So the design stages included storyboards, paper prototype testing, and then finally some digital prototyping. And we have to say that for the UI part of this, the Windows mobile development environment was quite good for that. So that's a storyboard. So those are little mock-ups that were done on transparencies, and you could try to develop scenarios and see how they would work to try and debug things before you actually implement them, because it takes time to implement them. And then this is sort of the basic interface that we came up with. It's not totally implemented yet, but it's pretty close. And so there's two views you can have on your cell phone, either horizontal or landscape or portrait, I guess would be the ways to say that. And there's you can use your stylus on the phone to do actions. You don't have to use the buttons. And there's some things on here. I don't want to say too much, but there's sort of a status line just below her, and then below that is the menu. And here we have inset. We have me, say if I'm signing to somebody else, and then the other person is big. And here's sort of a split screen one with the same size. And here we can add, you can type in and chat if you want to at the bottom. So we wanted this thing to have the ability to do chat as well as video, because sometimes the video doesn't come through at all and you need to do the chat. Yes, in the back.
Did you prototype that all on a smartphone device? So
Yeah.
This is the PDA
Yes.
version.
Maybe you can start it. You can start it up on. Is it around somewhere?
Oh, yeah, sure.
She can start it up and show it to you.
No, that's a PDA that doubles as a phone. I'm talking about.
That's a smartphone.
It's a pocket PC.
No, that's a pocket PC that doubles as a phone.
Oh, I don't know the difference. I mean, they're both phones and they're both PCs.
One difference is the cost, barrier to entry might come into
Yes.
right? Because I know sidekicks are cheaper than PDAs. Smartphones are cheaper than PDAs as well. But the screen size is smaller on the smartphones, but it's more of a phone that doubles as a PDA.
I see.
As opposed to the PDA that doubles as a phone.
No, we didn't do it on a smartphone. Just on this thing. And here's sort of the way you dial, sort of a keyboard for dialing. And instead of doing a call, you do a sign. So instead of talk, you have sign. So some future things we're doing, or current and future things, dynamic region of interest. And I have a demo for that too, just showing a skin detection algorithm. Objective metrics. Well, we'd like to have some objective metric for whether it's understandable or not, rather than just having people come in and say, because in real time we'd like to be able to adjust the video to make it more understandable, so we need this objective metric. And maybe we can even use the objective metric into the optimization process, put that into the optimization process. So a standard metric for quality is this peak signal to noise ratio, but we'll see in a minute that isn't necessarily the best. Also, activity recognition, we'd like to know whether the person is actually signing or they're listening. Because if they're listening, then we don't have to spend so much time sending out lots of frames. We can reduce the frame rate, reduce the outflow, reduce the work on encoding, and just spend time on decoding, and vice versa. Also, if they're finger spelling, then you might want to make the focus move from the face to a little bit more or wider to include the hand. Because finger spelling is usually done around here, right around here. And then we need to build a system. You know, we talked a lot about encoding and decoding, and we're working on that. So for the dynamic region of interest, there are some algorithms around, but they're not perfectly good. If we get to, the person might be moving. Signing, you actually do move around a little bit. You don't want to move too far off the field of view, though. But there are these fast skin detection algorithms, and we've been testing those. So I thought I'd just give a quick demo to show you that they do work. I think this is the last video. Let's see, this one. So on the bottom down there is what the skin detector found, and it's fast. It's fairly fast. So this is kind of the perfect situation. You have a neutral background. It doesn't have any skin tones in it. The clothing doesn't have any skin tones in it. And so it seems to work quite well in this setting. And our colleagues at Cornell have the principals working on this. I think I can close that whole thing now. So the objective metric, well, we already know the face is very important, the hands are probably important, and there is a signing box. So maybe we could use a weighted mean square error based on where the pixels are in the image. And so we did that. And so this is our kind of our comparison point. So this is Anna's data are the blue dots that tells you the understandability. And on the x-axis, on the y-axis is the peak signal to noise of those. So they are somewhat correlated. So the higher peak signal to noise, generally, the higher the average the understandability. But there is quite a spread there. So this R value tells you how much spread there is. So it isn't perfect, but very good. And we developed this little formula. I say Frank developed. We call it Frank's formula, or Frank's metric, internally. So we just looked at the pixels around the face, call that F, and we took the mean square error of that, and then we weighted it by 0.6. And then we took the mean square error around the head, around the hands, H is for hands, and we weighted that by 0.4, and then we weighted everything else 0, which is probably not a smart thing to do. And we basically, this is the PSNR formula weighted properly. And then it's more tightly correlated with this metric. So that's kind of evidence that, again, sort of confirms the eye tracking data, doesn't it? So it's more evidence that understandability has to do with what's around the face and perhaps what's around the hands. So there's a more tight correlation. So activity recognition, well, I mentioned that a moment ago. So fingerspelling requires a higher bit rate, or maybe frame rate, because fingerspelling seems to be a higher frequency than the normal signs. So we'd want to minimize encoding complexity when we're not signing, or not fingerspelling. So we'd like to recognize in the video quickly what's happening, what is the activity that's going on, and perform recognition in real time. Now there's a large body of literature on sign language recognition, which is, I don't want to call it a dead end. It's not been very successful yet.
A quick one. When you said your weighted mean square, your metric, you had a part for the head and a part for the face and the hands. Did you have an object, a shape of hand recognition, or it's more like skin that's not face than you call hand?
Yeah, the face would be just the face, and the hands would be the hands, and then everything else would be nothing. We're not going to count at all. But no.
Or skin.
No, but we can't use the skin detector alone. We'd have to add more to that to be able to detect that metric, to be able to use it.
You actually had some actual.
No, we don't. No, we did that by hand.
By hand. Oh wow.
Yeah.
Oh. So that would be something you would need to do something more automatic.
That's right.
Yeah.
Right.
Okay.
You need to be able to distinguish the head from the hands.
Okay.
That's an interesting problem. Because I think it can be done because the hands are definitely moving a lot more than the head is, moving longer distances. It's a tracking problem. Let's see if I finish this. So we want to recognize these three states, fingerspelling, signing, and not signing, and perform this recognition in real time. And we're moving along that, and Neva is working on this. He's here today. So our first approach is to use the H.264 motion vectors as features. So here's an example of some motion vectors. So I'll stand behind you again. So here's a little arrow right here showing that there's some movement, and it turns out to be your elbow here. And here's some longer ones here, and so on. So maybe we can use that information to tell us what's going on. That would be nice because we're already computing that for the compression. And then use probabilistic techniques to automatically recognize activity. And this has already been done in other fields, so it should work in this one as well. Hidden Markov model, Kalman filters, or particle filters. Particle filters are probably too slow, but so we're just building up on that. And this is kind of where Microsoft comes in, and that's why I want this video to go out to more people within Microsoft. So building the system, we're really just starting that too. We've done mostly data compression for the last year. We're only in the second year of the project, and so we developed everything in the what's it called, Windows Mobile. What's the development environment?
We're using Visual Studio.
Visual Studio.
We're using C# now.
Yeah. So we used C# for everything up till now, until we learned that we can't really use it very well to do this integrated system. That it's too turnkey, it doesn't give you enough flexibility. So developers can only use their predefined interfaces for the camera. Now maybe we don't know about some other things that exist that we don't know about, but as far as we can tell, the camera is only dealt with in certain ways and not in the way that we would like. We'd like more flexibility. So we can move to the C++ environment to do that, and the GUI development becomes more complex. In the C++ environment, it's not as nice as in the C# environment. But now, in this environment, we can access the things in the camera that we need to actually interface with our user interface. So this is probably where we need some education from Microsoft and get some cooperation with Microsoft so we can learn better how to build the system. Yeah?
I don't think you have to choose. I think you could write a C++ application to do the camera bit, C# for the rest.
Well, they have to work with each other.
There are ways
You can interrupt.
They will.
They can interrupt? Where's Carl? So is there, maybe somebody can send me an email as to who we can talk to about that, how that, okay? And so we already, Eve Riskin is here, is one of the co-PIs on the project. Sheila Hamami in Cornell is another co-PI. And Frank C.R. Mello is also at Cornell. And then we have a bunch of graduate students working on it, and some undergrads as well, including Lauren Merritt, who was one of the developers of X264, and all this is funded by the National Science Foundation. So any questions? Any more questions? I didn't go too far over, yeah.
All of the videos that you have shown and I guess have tested with were set up for very standard ASL environment with a one color background. Yet the feedback from the focus group was that they would like to use this anywhere. Certainly the background, when it becomes more complex, requires more power in encoding. So have you...
Especially if things are people walking behind you. Or
exactly.
Things like
Do you have any data of the impact of that on frame rate and the other parameters?
No, we don't.
Okay.
No. Yeah,
I mean,
Eve has something to say though.
I mean, it'll certainly mess up your quality having
Sure.
all that movement. But our answer to that is like when you use your cell phone, you don't use it here, right? You don't get reception. So we believe that the users would be willing to perhaps go find a quiet place where there's less activity when they use their phone. The same way I have to go outside to use my cell phone because I don't get reception here.
That goes against what the focus group said, though. Specifically, they said, we would like to use this everywhere, at the grocery store, on the bus.
Right, but you could go, I agree with you, but we don't always get as much, access with our cell phones.
Sure.
I agree with Eve that it will affect it quite a bit, but we don't know how much. That's a good question. We did have some videos, by the way, where we purposefully had people walking in the background, but we realized that everybody that walked in the background, we had their permission to be able to display the video. So, you know what I mean? There's some limitations to doing it in the sort of study sense. Yes?
Yeah, and the phone that was going around the room. One thing I noticed was the little bit maybe one thing we could think about is including the contrast on the phone, including the contrast, so that we can see more between the reading and the background. You know what I mean?
Do some separation between.
Yeah, right.
That's a good question.
That might be a solution for the background, if
yeah.
we were maybe fade out the background.
Right.
That would be
so this that would.
That idea. If you could give the users more control.
Mm-hmm.
More control for the contrast.
Right. Yeah.
So the users could adjust it for themselves to whatever works best for them.
So let me answer. Those are really good points. There are techniques for doing separation for background and foreground We haven't tried those. So most of the ones I know are really computer intensive and can't be done in real time. So it'd be very difficult, but maybe something could be done. As far as the second part of that is that there is, I didn't tell you about all the buttons, but one of the buttons on the user interface is options. So for example, we want people to be able to, if they want to do a smaller one and have it more clear, give that option. Or to make it black and white instead of color, give them that option. So there will be options there because we don't know what will be best. And this is very different than the video phones that are out there today. I don't know in Windows Live Messenger whether or not you can do even that. I don't think you can. But when you have this very, very low bandwidth, then maybe some of these options are important to allow that to have clear, but say black and white. Yeah.
So something a little along the lines of what people are asking for here is separating. I could imagine that the receiving end could click on a few points to say this is what I want to enhance or to fade back. A little like, I don't know if you've ever used PictureTell for conference calling, where the receiving end can direct the camera on the far end. Here what I'm saying is I'd like to say, I want to say that I'd like to see this a little sharper or that a little less sharp.
That's an interesting idea.
Or if I just clicked on the face and said this is the face or these are the hands, and if I get them in one freeze frame, then you could probably figure out where they're moving.
Interesting idea. Yeah. Yes.
I think you mentioned this early on, that you focused your data here on the power required to encode.
Right.
Do you have any information on how much power is required on the decoding side relative to the encoding? So it might make it easier if decoding requires less intensive computing resources.
It does, yes.
Okay, then it might be possible on the
quite a bit less,
receiving end.
a lot less. You know, it's 50% or more, 50% or less. And I think my understanding is that the cell phone industry is adopting H.264 and are building hardware decoders for that. That was one of our meetings with Singular. They talked about that. Yes?
I'm wondering how do you approach your research and the applicability, how this could be applied to other scenarios? So, to take advantage of what you guys are doing, but for other scenarios. So I'm thinking, like, if I'm communicating with my son who's 3 and he's jumping all over the place and he's very mobile, maybe I want to focus more on his hands more than on his face. So when you talk about like what options you give to the user, I might want to do different types of options when I'm communicating with different people. So, we're an accessible technology group in Windows. We're always thinking of how can accessibility scenarios also be applied to what we call mainstream scenarios. So do you do that in your research as well? Maybe you could just give us some insights into how you kind of formulate your ideas and the direction and how we can help mainstream some of this to get more traction and more attention.
Yeah, first of all, there'll be a default mode where it's not ASL at all. So it would just do video, just like it's done now, but not on the cell phone yet. So to answer your question generally, once this technology gets out there for deaf people, everybody will want it. Yeah. I mean, the grandmother will want to talk to their grandchild. Of course, that will entail including voice, which we're not considering. So we probably should add a voice channel to it as well. So I definitely support that idea. If it's a good idea, whatever you develop, if it's good for everybody, not just that disability group, then you should kind of move in that direction if you can. Because otherwise it's too expensive. The disability groups are stuck buying this expensive stuff just for them. So if it's more ubiquitous and everybody can use it. These phones in Japan that everybody has with the real-time video capability, everybody has them. Right? It's not just the deaf people. Yes?
Could I get some more information on your development environment? I know you said you're using Visual Studio. Are you also using like the mobile 5.0 SDK? And that's how you... now, is So when you're looking for help, you're just going to use like the default MSDN that's available in Visual Studio. Is that what you use when you're porting from the open source into into a Windows-based?
Oh, that's a really good question. We haven't ported the open source stuff.
Oh, you haven't done that yet?
The interface right now is just a prototype. It doesn't actually do anything other than moving boxes around.
Okay.
But that's going to be a big issue when we do want to start importing like the codec and things like that. Right now we're still struggling with interfacing to the camera in the way that we want to interface.
All right. So, but for now, you're just using the SDK, the mobile SDK in Visual Studio. Okay.
If you have advice for us.
I work on the platform builder team.
Ooh,
so
good.
That's kind of why I was wondering what you were working with, and I'll get some names of people who can help you with like that. They interoping between C# and C++, and also hopefully help your development experience a lot smoother, make it more smoother.
Great, well, thank you.
Okay. Well, thank you. Thank you.